All right. So we're going to do the lab today, and then we'll jump back into homework stuff here. I think I'm better prepared now than I was because I looked at the answers and I understood what I was going for here. So for this lab, we're just trying to find how much paint does it take to do this podium, essentially, right? Now, the second last question here. No, I think it's the last one. The last one, it says, can you just approximate this? Now think about it. If you're looking at this thing from the top, couldn't you just say, oh, it looks like a circle? And if you wanted to look at the sides, can you say, oh, it's kind of like a cylinder? And then you can approximate and get an answer like that, right? So do you need to do this to find how much gallons of paint you need to be buy? Probably not, but we're doing this because it's mathy. Okay, cool. So we want to be more specific. And now I do want to say, because I'm recording this and I don't want to give exact answers, I'm going to use a different A, but the B is going to be the same. I think everything's going to be fine. It's just, you change a little bit and it'll be okay in the end. Okay, so my A is a little different when I'm working the math. So this is the formula basically for what we have. I just rewrote it more pretty, X, Y, and Z on its own lines again, so it kind of looks pretty. And we're going from 0 to 2. And I don't necessarily need to graph it right now, but I do want to find out how to get the areas. So it says, what's the surface area of the top? And then what's the surface area of the sides? I think that's really the big thing, because after that, we're going to add them up, and then we divide, and we're done. Okay? So these are the two big problems right here. So if you want to look at the top, this is what I would use for the top, is this formula back from, I think that might be Cal 1, but definitely by Cal 2. It's not just surface area, it's just area. It's area of a polar region, okay? So this is an older formula that we've had before, but don't think of it like surface area, just think of it like area of polar region, okay? So if I'm looking at it from the top, and I'm going to go back up to my little picture here, this is what we're looking at here, okay? I'm looking at a spiral, but, oh, I went the wrong way with the spiral. It's okay, we'll get it. Hold on. If I do this, there we go. What we're doing though is we're getting different r's as we go around. So it's like I start with r equals something, and I'm going to go 2 pi, yeah, and then my r will end up being something else. So is there a formula where I can change my radius as I go in a way? Because that's all I'm doing. I'm just changing this number a little bit as my theta grows. You get my point? Okay, cool. So where does it start and where does it end? What is this smaller number and then that bigger number in a way? So let me read a little bit, okay? So it says bird's eye view, we got a feet across. Okay, see the initial radius is a. Do you see that? And the height is only 1 foot high. Okay, cool. Oh, and B is the width of the ramp. Okay, so A is the initial radius. So in a way, let me blow this up here and do this. This right here is A, and then B is this amount right here. Not the full distance, just that little tiny distance, right? Y'all feeling me on that? What would then be a formula for my radius to change as I go? Okay, there we go. You're wanting to combine them, right? You're wanting to go you're wanting to go from A all the way to A plus B. So okay, let's do some math here. So initially, my radius is an A, but then my final amount should be A plus B. Now, time-wise, I started at 0, but then over here, it should be 2 pi. Yeah, I'm going full circle. Now, if you wanted to just say 2, that's fine, but then you would have to think about the formulas to get the pi out of it eventually, right? So I'm just going to go very basic. Now, I know that like my original formula says, oh, we're only going from 0 to 2. That's for this huge big formula here. We're not really doing that right now. We're like taking a part of it in a way. Okay? Like I'm just saying, like analyze this as like a seashell. Stop looking at everything big and just look at the seashell. Okay? Seashell? Seashell. I said it right. Sally sells seashells at seashore. So how can I put this into a formula? That's the thing. That's my big question here. How do I make this into a formula? Give me some ideas. What if I didn't call it final? What if I called it terminal? There it is. We're getting somewhere now, right? And what does terminal minus initial give you? It's kind of like a slope in a way. So let's go back to our like original line formula in a way. It looked kind of like this, but rather I can make it better. I could say it was initial plus terminal minus initial times t, something like that. It's kind of like the updated version. I'm starting with an A, and then here I'm going to be adding more into it. I want to say I'm going to go from 0 to something else here. What would this end up being this time? This whole thing? A and B terms. What would that end up being right here? If this is just A, what would this end up being? Just B. Just B. Because if you think about it, I'm starting with my initial ramp and or my initial circle, and then I'm adding the ramp as I go. You basically just made a formula. Now, there's a little bit of a hindrance here because I'm saying that my time is going from 0 to 2 pi. I want to go the full circle, right? But if I said multiply by 2 pi right here, I would be saying 6 times b. I don't want to have 6 more of them things. Like, I don't want it being that big. See, that's like 6b. Do we want it that wide? So how do I reduce this down a little bit? You're dividing by, say it again. Basically, you're dividing by that 6. You're dividing by the 2 pi. Because when you plug in the 2 pi, then, and I say 6 because it's 6.28, but yeah. But exactly, when you divide by the 2 pi, then your t kind of like nullifies itself. In a way, if I say plug in a 0, you get 0. You plug in 2 pi, now you'll get that 1 that you're looking for, that 1 times that amount. And so this is my true formula. So let's like put it all together now. So I have my area is 1/2 times integral 0 to 2 pi of this guy. Oops, it was an A, not a B. I can't use A and B. I need to use 10 and 5. But now that I told you, I'm going to do it. dt. Desmos. Right, Desmos. We don't need to sit around. Oh, wait. There's something missing. It's squared. It's squared. Bad Chad. Correct. That would be the radius as I go. I'm going from radius of A all the way out to a radius of A plus B, essentially. And when you plug in the 0, when you plug in the 2 pi, those should give you A and B in the end. So in my case, again, mine, not yours, I'm using a 10 and a 5. You're using a, well, I'm not saying it. But you can. I'm fine with you saying it. Oh, thank you. Look, I even talked about it. Thank you. So happy you told me. So I got 497.418, and this is, I think it's feet squared. I can't remember if it's feet or something else. Feet. Yeah, it's feet. I'm sorry, but we're here in America. Oh, that's funny, but it's gonna happen. So, anyways, that's feet squared because again, it's an area, right? So that's how much we have for the top. Good so far? So that's like what I would put here in my first one. Is okay. Are y'all good with this? Where I can now erase it to get to the next phase, I guess you can say. Good. Okay, excellent. So I almost have to erase everything. Not really. I do want to keep this, and I just want more room. So we don't need this anymore. And this picture doesn't make any more sense. But that formula there, the second one here, what is that formula? And y'all that were here way earlier, you heard me say it right there. What's that formula right there? Practically, but it's yeah, FDR, exactly. is also just a plain line integral, as in like from 16.1, right? And we were looking, and I have it up here so you can see the line integral formula. What I'm looking for is exactly this. I'm looking for the area of a curve as it goes around. What is that curve that's going around? Voila, right? So we're like super close. All we have to do is kind of put them in the right places. Okay, so because we have a v, obviously we're going to have to find our derivative of that thing. I'll wait. Can Desmos do derivatives? So let's do a little bit of this. I got my cosine right here, and derivative of cosine will be, okay, so I got a negative 10, and again, I'm doing derivative, so I have a 2 pi is in the front, and then I have a sine of 2 pi t. That's for this one. I'm basically distributing this. So then now I have product rule. Okay, so now I have a minus 5 times product rule. I'm going to leave, I'm going to take the derivative of t, so I get a 1, leave the cosine alone, plus sine, and then I leave the t alone, and I take the derivative of cosine, turns into a negative sine. Very good. 2 pi sine 2 pi t. Whew. Comma. That was just the first one. And that's okay. I mean, the lab's got to be a tiny bit on the hard side, right? Same thing with this one, though. It should be pretty much the same thing. My derivative of sine would end up being a cosine, and a positive cosine at that. So I actually can just practically do the same thing, as long as I'm going to keep that same flow. Here, I'm going to retain what I have. And then here, it's now should be a positive, and then again a cosine, comma. All right, help me out. What's the derivative of this last guy? After all that, yeah, I'm happy to have something a little bit easier. Okay, so that looks pretty horrendous. And now we're going to square them and then do the square root of all that. Yeah, Desmos. Heck yeah. So we're going to do some Desmos on that here in a few seconds. But we need to, I'm not worried about this now. Basically, I'm going to plug that guy in. Everything will be fine. It's a lot of typing, but we can do it. I'm worried about this. Okay. Now, one other thing, it said I'm going from 0 to 2. So like that was fixed. And so again, all of this is good. All of that's good. I'm worried about this guy. What is the function? Or essentially what I would say is, look, it says right here on the picture, what is the height? What is the height? Say it again. Well, think about this for a second. Let's go back to the pictures. It's not a constant 1 foot high. You see how the ramp right here, it starts at 0 and then it builds up, 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 up. That's that. This is that curve, by the way, is that curving around thing. Kind of. That's a good idea there. Okay. I like that because it's only 1 foot at the top. Like the total distance from the bottom to top is a 1. But like I need to know what the height is as I'm going, right? Okay. I like what you're doing here together. So this is basically, it's going to be a formula of some kind. We're going from 0. Let's start it again, right? Let's do the initial thing. Initial terminal. I'm going from 0. Oops. I'm going from 0 feet to 1 foot. And my time was 0. And here my time is 2. How can I express that as a formula then? Yes. Yes. Do you want me to do that? Initial plus terminal minus initial, and then times t. Okay. So what would I put for initial? 0. And then terminal? 1 minus initial. Seems kind of easy, but remember that we're having to plug in a 2. So if I plug a 2 in right here, I'm saying 1 times 2, that's 2 foot tall all of a sudden. That doesn't make sense. So what can I do to make this better right there? Divide by 2. Very good. That was exactly right. Divide by the 2, just like we divided by the 2 pi last time. So now my formula ends up just being 1/2 of t. That's kind of easy. We like that. Now there's a small catch to this. There's a small catch to this. How many sides are actually described by that? In a way, I have to peel this apart like an orange. So we have this ramp going on, and so I have this ramp coming up like this, and then it kind of comes out like this, and the amount that you're seeing actually ends up looking more like this in the end. The reason why is because some of it's already covered. If you're peeling it apart like an orange, it's not just one triangle anymore, if that makes sense. It actually kind of like it's behind a wall. Some of it gets eaten by the wall. Okay, so then how can I, what am I doing with that then? Isn't that interesting how that works? Here's what I'm thinking, is that there's actually the original that we have here, right? That's my actual height that I'm kind of finding, I guess. But then I have some of it on the bottom here. It's like I'm either cutting it in half or I'm doubling it or something like that. I think we're halving it. But then is the half already taken care of? I'm actually at a point where I can't remember. I can't remember what my lab said, but I'm sure that what I had put there was something like I had to cut it in half in order to make it make sense. It was just a half, but I can't remember if I had done that already here. So here's your goal in this here. I want y'all to kind of think about that as we go, because I can't give you the answers entirely, right? I want y'all to learn a little bit of concept. So there is a question mark. What goes in the front here? Okay, it's either a 2, a 1, or a half. It's something like that. But then I have half times t times, and here we go, square root of blah squared, blah squared, blah squared dt from 0 to 2, and now go and do it, right? I'm going to go and do it with thinking there's a 1 in the front, and all you have to do is either double it or half it, depending on how that you see the concept. Is that okay? Cool? Okay, cool. So I'm gonna do that huge thing on this side here. So here we go. Yay. So I'm actually kind of happy that I forgot what I put in my solution, so that y'all can kind of struggle a tiny bit with that, okay? But I think everything else we've been doing is fine. We did the math fine. This is a concept. Are y'all understanding? Are you good with it? So from what you're saying with that, basically try and find which the rate that it increases on the ramps, like, and essentially, like, since not one foot like the rest of it, we have to calculate the slope of it essentially. Well, the slope's already calculated, I think, with the half. Like, we know for sure we did the math, and this is good. I'm not sad about that. I'm thinking that because some of it's disappearing behind the wall behind it in a way. Like when you're looking at it on the side, there's something missing in a way. Now we can definitely check by doing approximations and check, like, I mean, we're approximating it as a cylinder, right? And if you look at it on the side, if you go back to the pictures and you look on the side, it's practically a cylinder. So if you get something that's not the same as your approximation, maybe you need to double it, maybe you need to half it, if that makes sense. And because we're looking at it differently. Are you seeing like where this point right here on the end this point at the end here, how it's going around the outer edge. And so that looks fine. But there's this point on the inner edge also. Yeah? See how that's kind of making the side up this way? I think we're going to double it. I think I'm going to end up doubling it because we got this outer edge here. And then it ends up that there's just like this inner part too, this inner edge. Well, yeah. So I want y'all to think about it a little bit. I think it's double, but I'm not entirely sure. Let's go and do the math and just go through it, okay? So here we go for the next hour. I'm going to start typing this. Yeah, everything's fine. As long as I remember to square it. Because, you know, key little pieces in there make the whole big difference, right? Too much time. I'm so sorry I denied you, bro. I'm just gonna do this because I'm basically done right now. And again, I think that I need to double it. And so I'm gonna assume for a little bit that I'm gonna put a 2 in the front. And we're gonna check it against some approximations, okay? So I'm assuming right now that I'm using the 2. I did all this and I got a 44.1156. Again, y'all are getting different numbers, but there we go for me. Cool. Did you write down my numbers for last time? Because I already erased them. Did anybody write my numbers? Huh? No. Like the first integral that I got, it was like 200 something. Thanks for your teamwork effort here, guys. Man, 2.1156. Okay, fine. So I'm adding the other guy, right? So that was 1/2 in the front, integral 0 to 2 pi of times 5 times t over 2 pi, like that? All squared. Did that again. Okay, was that it? Does that look right? Okay, cool. So I add them together. So that's your number 3, is you say plus. How nice of you, Chad. And then the last one is going to be divide. So if you go back to the assignment here, it says you got 400 per each gallon of paint. So then if you look right here, again, your numbers will be different, right? Because I changed my number significantly. I'm taking that value and I'm dividing it by the 400. So I get 1 point something or other. I think you all get like a lot more than that, but you know. So answer divided by 400. Why did it not do the answer? I'll just type it. It's fine. Maybe it's because it's in graphing mode. I don't know. Okay, so 1.35 gallons of paint for mine. You're definitely not going to have that. It'll be something else for sure. Did it say round and nearest whole number? Okay, cool with that. So then talk about it, approximate. And I do want to do a little bit of approximation with you guys. So I'm going to clear everything and just do some rough approximations. Is that okay? All right, here we go. Clear it all out. Boom. So if I was to approximate this shape, I would say it's a cylinder, essentially. So I have this here. And roughly the ramp, let's go with half of it. Because like basically halfway through the ramp. So I had 10 and then an additional 5, right? So let's cut it in the middle here and say 12 and a half. So I'm going to say my radius is 12.5. And so then I got pi r squared, and you're screaming at me, hey Chad, that is so much easier than what we were doing. No painter would ever do calculus 3, you know? I should have kept my answers yet again. Did y'all write them down this time? No. 497? Pretty close, huh? Pretty close. So that's just the top. And then the cylinder edge, again, we know that that was supposed to be 1 foot, right? Generally. So then I would do the 2 pi r, which got me 6.28. Why did I put a pi there? I'm sorry. Right? Oh, no. 2 pi RH. It's 2 pi RH, isn't it? 2 pi R was my 12.5, and then my H was a 1. It's 2 pi RH. What did I get for that one, by the way, originally? 44, okay. So notice that it's kind of interesting. Mine's almost double that. It makes me wonder if I needed to... Did I multiply by a 2 in the front? All right, whatever then. So this is just approximations. But when I take these and I add them up together, 490.87 plus the 78.539, I got 569.409 divided by 400. And this is so silly how it's practically the same. Right. So when you're doing paint, do not do calculus 3. but it's fun to see how we're using these structures and getting exacts. And there will be times maybe in your life where you do need an exact answer. You're not just slapping paint on it, it's doing something else with it. Cool? Okay, so then yeah, that's a talk about it, but now you kind of get the picture of what I'm doing there to do that talk about it. Any questions? Yeah, they're really easy formulas. So that was an easy formula, that was an easy formula. Yeah, pretty cool. Well, not really. I did halfway in the middle of the B. Yeah, I said A plus B over 2. But again, you could probably do A plus B. I don't know. That's maybe why my cylinder one is a little bit more off, because I'm using something that's not quite right. Because if you notice, if I went back to the plane 10 with that, I probably would get a lot closer answer. 62, and it was supposed to be 44. Well, I mean, I just think that there's something I'm not seeing. So y'all go back and check some of that stuff, but that's the rough way of seeing it. Cool? Good enough for the day. Yes. Here, let me kind of talk about what I'm thinking. So we have this part here, but then we actually have a whole other ramp part that's like this going around it. And this is the actual ramp entrance. And then you're going around, and then you're like getting to the podium circle right there. So you actually have a lot more surface area than what we normally would just see. Maybe I needed to double it again. I don't know. I'd have to look into it more. But that's y'all's point, is that I'm giving you most of the tools. Go and find out what you think about it, Spend a minute or 2 or 10. Cool? Okay, good enough. Now, off to the homeworks. Yay! Homework time. Ba-dum-bum, ba-dum-bum. You tell me where to go, what to do. I'm here for you first. And if not, then I got plenty of problems I can do with you guys. And thank you. Okay. Got something for me? Oh. Oh, okay. Okay, okay. Mm-hmm. Sign to the n power? Uh-huh. Uh-huh. Oh, that's good for them. I'm I would just because I'm more of a formula person. When I see sine to the fourth, and it's especially during an exam, I ain't got time to try to think about it. I got a formula, pop it in, you know. Um, but yeah, there's the tricks that make that work better. I just yeah, it's up to you. That's what yeah, you're calling that one. We can all do trig subintegrals, right, guys? You went through Cal 2, right, guys? That semester was kind of a blur, Chad. Oh, okay, fine. Thank you. All right. You got something for me? 16:4, 14. Going. All about it. Love doing homework problems. So it says green check mark was something I was doing. In fact, this is 34. That was going to come up eventually. So perfect. I love doing it. Let's do it. Yeah, this one was confusing, mainly because it had like blip, and I'm like, what is going on? Like my other problems don't have that. So yeah, let's talk about it for a while, and let me minimize that thing and do a little bit of this. That'll work. Be good enough. Okay. So let me write that down, and I can kind of like full screen here in a second. So it's not R, it's area of the region R. So area. 1/2 integral x dy minus y dx. So that's what they're wanting. They said x is equal to t sine of t. Then I got 1 minus cosine t. And that's it. Perfect. The only reason why I would keep this on the homeworks and exams is now that you have Desmos graphing, right? I don't know what that is. What did they say? Was it one cycloid, one arch of the cycloid? You know what I mean? Like, what are you talking about? So let's do some. Oh, you know what? I have a Desmos right here. I don't know. So yeah, one arc of it, half circle. That's I'm loving what you're saying. So let's like do that. To do parametric equations, you have to do parentheses so that it looks like this. And then you get to pick 0. I'm going to do like pi, I guess. Okay. But that's not fully completed. 2 pi looks like it's a full complete arc or arch. So that's what I'm going for. I want to basically say 1/2 integral from 0 to 2 pi of stuff dt. That's going to be my goal here in a second. Yes? Good. So I have x and y, but what would be dx? 1 minus perfect. And then I would have, oh yeah, y'all right. I was gonna say 0, but you're right. Positive sine of t dt, and now I'm just gonna plug those in. So then we get x is t minus sine of t. And then my dy is a positive sine t dt minus my y dx. I ran out of room. Yes. No, it's too messy. It's not right. Man, bad Chad. Starting over from the beginning. Yes, that was a positive sign. Minus, and then y, then dx, and then all of that dt. Desmos. Definitely Desmos on this guy. I love when there's answers like that. What? Are you saying that we need to do it normally good and blah, blah, blah? No, I'm saying divide by pi. Of course. Of course. And of course it's going to say, no, that's not the right answer. Is it the right answer? It's supposed to be positive? Oh, it's an area. That, yeah, okay. I would say that. Yeah, it is that way. I wrote, yeah, I basically just said negative 3 pi, positive 3 pi. I didn't even put words for it, but everyone knows. Okay, cool. Does that make sense? Is that good? Yeah. Yes. I don't know. But see right here, and then right here. Oh, yeah. Really? I'm sorry. Did you not bring your like energy drinks today? We got coffee for you. Do you like black coffee? Because there's no more cream or sugar left. It's just me and Lee drinking it all. Yeah, yeah. Pretty much. Give me some more. If you want me to. Oh, yeah, of course. Okay. Yes. Uh-huh. Uh-huh. I've especially went through all the questions so that you don't need to be using Desmos graphing. It should be obvious. Yeah, like I know what you're talking, especially the cardioids are not there, the cycloid thingies are not there. Like this one I wouldn't have known, right? But that's not on your exam. I specifically went through and removed that stuff. Right, Mason? There we go. Yeah, no leafs, nothing weird. It will be, if it's converting and you need to know region, it will be obvious. Yes. It's a good question, Very good. Yeah, I specifically know you can't use Desmos graphing. The heck if I know what it looks like. So yeah, we're not sitting there trying to figure out pre-cal. We're moving on. Very good. Good question. Okay. Give me some more or I'll start doing my own. I got plenty. Okay. Is that the sign of come on, Chad, let's do something, right? So I'm gonna do 16, 4, 15, unless I don't know, did I do this one with you last time? I don't think I did. So one of the first things is that there's two answers and I mix them up. So, if one doesn't work, try it on the next one, it'll be fine. So yeah, let's do this one here together. Okay. So there's two formulas. They're doing the flux formula and the circulation formula. I have to go look at those because I can't remember. This is the stuff that I'm writing down on my note card for my final, Say that again. Well, for recording purposes, I'm showing them that I don't know what I'm doing. Right? Okay, cool. So yeah, we're looking here. We got the flux and we got the circulation, right? So when I go back to the homework, let's make sure they want flux first. So I'm going to write that one down first. Flux first. So here we go. I got the flux is double integral of mx plus ny dA. And then that circulation is the other guy, nx minus my dA. I love when it's two-dimensional, man. Look how easy this is. It's funny to say that when we're doing calculus 3 and it looks all crazy. Look how easy that is. You're like, oh yeah, no problem. No problem. No problem, bro. We got this. No problem. So we got m, we got n. So my derivative in terms of x, so the first one is 2y. Correct, plus 0. Yeah, I was thinking there was something else. Very good. And then plus, now this one in terms of y would be a beautiful. And we'll come back to that guy in a minute. Let's get this guy now. So derivative of the second one in terms of x, 2. And then minus sign. Now we're going to do this in terms of y. There you go. 2x plus 2y. Correct? dA. Squeeze it in. So the only thing now is that I need to find the region. And you can see that we got a top and a bottom. Now, when I'm doing this, I'm going to go, my bottom would be x squared, and my top would be, there you go, square root of x. Because again, I'm square rooting both sides. You have to do it in terms of x because this will be 0 to 1. Blah, 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 dy dx. Yes? Okay, good. Okay, so same region for both of them. I'm just going to pop it in and hope for the best. Desmos! And then you do it again, and we get Desmos. I see the bottom and top, right? So my bottom is the x squared, pretty easy. The top, you would have to solve for it, right? But it's just square root both sides. Cool. Desmos time. Ba-dum-bum-bum. I know, right? Are y'all going to be singing that kind of stuff during the exam? Okay. Good. Will you be disturbing other people in the lab? Perfect. Perfect. That's funny. Oh yeah. I think I turned off the sound requirement stuff for that because yeah, it starts dinging stuff all the time. That's kind of funny actually. Well, I don't think it's test over, but they do send like the people. They'll like stop your test and say, "Okay, let's talk about it." A really funny story. I'll do this on a recording. The guy's sitting there like with like a drink, and he's like drinking it, and it's like it just shuts down. And he says, "Hey, yo, can we look inside your drink?" He's like, "Bro, I'm just drinking some." Because he thought there was formulas inside of his drink. It was like one of those big soda things, so he had to pop the lid and show them. It was hilarious. Yeah. So he's like doing the straw thing. It was so funny. But that's what they do. They're good about it, man. Like, let me see that cup. Kind of. It's like it's AI plus human. So the AI does it normally, but then the human jumps in when they need to. No, it's the company, but we tell them what to do. So yeah. Yep. Cool, huh? We got it. We're good. I can do more. Unless y'all got something, I got more. Sure. Oh gosh, cannot change that. I know someone else has set that, and I can't do it. I have been wanting to do that for years. It just doesn't happen. Yeah, at 11 instead of 12. Yep, something about it. My math lab, only my math lab does that. I don't know why. Yeah, it's very annoying. I don't know how to fix that. I've tried. It just doesn't. Nobody likes. I don't know me. Nobody likes me. Yeah, cool. Let's do it. 16.5, number 12. An hour? Oh, okay. 16.5, number 12. Look at all them green check marks. You know why? Do you know why? When you click on them, it's because I. Yeah, yeah. That's funny. Let's do it, man. I'm super excited. So find the area of the lips cut by this and that. Oh yeah, this is cool because what you're gonna find is it's a scalar. It's literally a scalar of the original ellipse. And like on videos when I'm doing these kind of problems, I can't really do the concepts that much because I don't have the time, and I don't even have time for this, but for the concepts. But I want to show you. So normally we're looking at ellipses. That's a circle. Whatever. So we got a circle. Yes, exactly. So that's the 2D version. And so it looks like this on the 2D plane. But on the cylinder side, the 6x makes it cut this way, I believe. This is not really what it looks like, but it's going to be something kind of like this in a way. So we're looking right here at this guy right here now. I'm wanting to know what that area of that thing is. But what's happening is it's the same thing. It's just a scalar off. It is pi r squared, but now I'm just putting an a in the front of essentially. I don't know what that is. You might be able to do like the arc tangent or something or other to get it. I don't really know. I think it's just tangent. But that's not the point. We're going to do the integral for it. I'm just saying this is a pretty cool thing that we do. Okay. So how do we do it? Surface area. I would say we have a surface area formula. I think it was fx squared fy squared 1 dA, like that. Okay, cool. So yeah, surface area. Um, this is what I would say is my f. Because again, if you notice, it has to be equal to z because the z is a 1. essentially I'm saying what's my derivative of the z? It's like dz is, they cancel and make a 1. I don't know, something like that. But what's my derivative in terms of x? And I square it, derivative in terms of y, and I square it, and you're like, what? dA. So you can see what I'm going to have. That's 37, and that's how they're going to get the answer there. And so I'm really saying here, the area times square root of 37. We know what the area, oops, what is that? Go away. Go away. Why is it not going away when I say go away? I don't want any of these. Leave me alone. What is... Anyways, so, yes, exactly. So I'm saying the square root of 37 times my area. And what's my area of that circle? It's pi r squared. R is 1 in this case, and so therefore we get this. So we did actually find A. It was the square root of 37 in this case. Pretty interesting how that works. Yes, definitely. But I mean, it would be a circle still, I think. I don't think on this problem. I can. I can. But even then, if you had an ellipse, or even if you had a rectangle, right, we can find area of things pretty easily. The concept is that I'm saying a scalar times the area. Cool. Good. 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 Give me another one. I got others, but I'm waiting for y'all. Darn. 16-2? Number 10? I think we did it before class. That's what James keeps talking about. But I will do it again because we're being recorded. It's 11:34. We're past time. I'm going to do this since you asked. Okay, where else are y'all going? Come on. Yeah, you know, see. And I have to go grab pizza. Gosh, Mr. Vice President, I tell you what. Yes. Do you drive? Cool. Can I give you cash? Oh. As if I have nothing else better to do. The main thing here is straight line. Straight line, which means y equals mx plus b. That's our R pathway. And so we're going from 0, 0 to 3, 9. Really, I'm going to not do too much math here, but it's this, and we're done. So you could do the point slope formulas and all this stuff. I don't really care. That's your answer. I. So we got this guy, and now I need to make an R from it. And so if I say my independent variable is the x, then I'm going to say that's a t and then a 3t, obviously. Again, this is x and y. Because we're going to do the FDR thing, I'm going to go ahead and find the prime. So 1 and 3, easy. The rest is just super easy stuff here. I got x times y. So I would have t times 3t. And then times the derivative is a 1 right there. Plus y minus x times the derivative dt from 0 to 3. Exactly. If x is equal to t, then it's going to be 0 to 3. Very good. Desmos. Perfect. So 3t squared plus 6t. There we go. We got it. Is that cool? Awesome. Yeah, straight line. That was our main hiccup this morning. Straight line. All right. Are we good with the recording? All right, good. I know we went over, but that's good, though.